Thanks everybody for joining. The topic for today's talk is implementing over-the-air firmware updates on STM32 H5 and H7 controllers. So the agenda for today's talk will be is first the short introduction about myself. Then I'll talk about the theory, how about different strategies implementing over-the-air update. And then at the second half, I will show a real implementation and explain it. But since the whole topic is really complex and you can spend days talking about the OTA. So I'll try to explain as much as I could. But if you guys have any questions on the way, please click on this Q&A button on the Zoom toolbar. So and type in your question. So if you have any question, if you want me to elaborate, type in the question and I'll answer that. So yeah, so let me start with that. Who am I? So my name is Sergey, and I'm the author of the Mongoose networking library, an open source a TCP/IP stack and HTTP WebSocket library. I'm also an author of bare metal programming guide on GitHub. I think that is the most popular published, at least on GitHub, bare metal guide. It has more than 2,000 stars so far. I'm also a speaker on various conferences like Embedded World and others. I am an engineering director at Cezanto, the company behind Mongoose library. And so over the years, myself and my team were working on different implementations of the OTA. And I want to share some of the experience that we've gathered on the topic. So I hope that will be useful for you. Definitely it'll be useful for the new novice engineers, but maybe some developers and engineers with with a solid background also find something interesting in this talk. So this is me, and let me start. So the first part will be the theory part, the different strategies, how the OTA can be implemented. And so by no means I will describe everything, because there are different strategies, and there are strategies that can be a blend of strategies. So the number of different combinations and variations is limitless, right? So it is impossible to name all of them. So what I'll do, I'll just explain and describe some of them, maybe the most popular, so to say, but definitely there are others that I won't describe. So let's talk about the simplest scenario. How do we want to update the microcontroller? So the typical microcontroller has a flash memory, either internal or external, and the firmware typically resides at the beginning of the flash. So what we want to update the firmware code, right? So and here on the diagram we have a typical layout, flash memory and the firmware at the beginning. So how do we update? Well, the most obvious choice is to split the flash into two partitions and copy the new version of the firmware onto the second partition, right? So this is the most kind of obvious way to update the firmware, right? So and then when the device boots, the device needs to know and needs to have some clue about what firmware it should execute. Should it execute the first firmware or the second firmware? And that knowledge is typically and the logic, the decision logic, is typically resides in a small piece of code, which is called a bootloader. So a bootloader is a piece of code that decides which firmware to boot. Sometimes the bootloader also does some other things, but for us, that's the most important thing. And there are two ways of implementing bootloaders. First way is to include the bootloader logic at the beginning of the firmware. So, and this diagram 3 shows that. So the cyan blob BL bootloader, it's at the beginning of the firmware, right? So when you copy the new firmware, you also copy a new bootloader. And the second way of doing that is to allocate a section at the beginning of the flash. Typically, it's on the beginning of the flash for the bootloader, and it stays, it doesn't change. And then the firmware, the partitions go after the bootloader, right? So that's the second way of doing things. For example, like on Arduino, if you take a look at Arduino, most Arduinos use the last approach. So there is a bootloader at the beginning, and well, there are no two partitions on Arduino. Like there is just one version of the firmware, but the bootloader stays at the beginning of the flash. The benefit of the third diagram is that it allows you to update the bootloader as well, right? So it's kind of the benefit, but also could be a curse. So if you make a mistake in the bootloader, then the whole update process may be may stop working. So this is the whole scenario. It looks simple enough, right? But now there is a catch with this. So what is the catch? The catch is with the so-called linkage, with the firmware linkage. So let me explain that. So what is that? So when we build any executable on the workstation, or we build a firmware, that firmware consists of basically just a bunch of functions and a bunch of data. That's what it is. And so that's an example. We have two functions, foo and bar. And then when we make a binary, the assembly instructions, the machine instructions, for example, function foo calls function bar. So it looks like this. The assembly instructions basically makes a call or branch or jump instruction to the address of the function bar, right? So when a firmware gets built, during the link stage of the firmware build, every function and every variable, they are assigned a specific absolute addresses, right? And then every reference to a variable and every function call, uses those addresses. So when a function foo calls function bar, it is a jump to this a specific address. So that means, so when we build a firmware, that firmware should be laid out in a specific flash locations, right? For example, if the flash is mapped itself on some memory region, then the addresses of those functions should correspond. So now if we make our firmware and we copy that firmware to the second partition of our flash, and our firmware, like function foo calls function bar, that the very first jump would jump back to the beginning of the flash, right? So this is the caveat with this approach. So the problem which I want to demonstrate here is that every firmware, when it is built, or sometimes they refer it to linked. So the firmware is linked to a specific base address. So all functions, all data, all variables are kind of like are relative to this base address. And this build mechanism, the firmware build mechanism, this base address is specified in a build instructions. It depends on the tool chain. So for example, if you use GCC, GCC uses so-called GNU linker script. So GNU linker, a program that builds a binary, it uses linker script to to specify memory regions of the firmware. Other tool chains like CLang or like IIR or others, they use different mechanisms, but the idea is the same. So let's take a look at the example linker script. So the linker script looks like this. I'm describing this because this is a very important thing to understand, right? So this is the example linker script. And as you can see, this linker script defines, let me increase the font. It defines a couple of memory regions like flash and RAM. And it says that the flash starts with this address and has this specific length. And the RAM starts with this address and has specific length. And then we specify that different parts of the binary, so-called ELF segments or ELF sections, this linker script specifies where each section go. Like specifically, we say that the vectors, so the vector table goes to flash. And this is the first instruction. So that means that the vector table goes at the beginning of the flash. Then text, which is code, then read-only data also goes to flash, and then we have data. So when the data goes to RAM, so it's linked to RAM, but it's concatenated into the binary file, which is written to flash, right? So this is an example linker script. Yeah, I'll probably show you how that works. As I mentioned, I'm the author of bare metal guide, right? So let me use that. So this is the bare metal guide. So let me clone that and show that to you how exactly linker script works. So I go and I clone this repository, the bare metal guide. And so I go to some simple project, for example, for printf, right? So CD steps, step 4 printf, right? So this is a really simple firmware, very simple bare metal firmware that just prints, blinks an LED. Yeah, it blinks an LED and prints messages to the UART. So so the main thing that we are interested in is that this is the linker script, right? So this is the linker script. It's very similar to what I've shown you. So that's the linker script for the STM board. And now if I make this firmware, you see, so I built it. Now the result of the build is firmware.elf file. So if I do obj dump -d, which is disassemble firmware.elf, right? So I can see like all functions here. And if I search for main function, then this function, where is it? So this is the function. You see, so this function, it starts from the address 80022C, right? So this is, so why this address? So how do we know that this is the address? Because the linker script tells us so. So if we look at the linker script, we see that the flash starts from address 8 and then 6 zeros, right? So that means all functions like main and other functions will be kind of like at that memory region. So I guess this is clear to you. So this is a really important thing to understand. So linking, and how the firmware gets built. So now we understand that it is impossible just to build a firmware and just copy that to the second part of the flash, because it won't work. The very first variable access, the very first function call will refer to the beginning of the flash and will probably crash the firmware. Okay, so what is the solution for this? So the solution for this is simple. So we have, for example, this firmware, right? So we have this firmware. I'll do it with that. So, and it is built using this linker script, but we may have two linker scripts. One is specify the beginning of the flash to this address, and the second linker script can have the flash base address different, right? It can point to the half of the flash. And then we build two firmwares using the same code, but two different linker scripts. So that means that we're gonna have two firmwares with exactly the same functionality, but they are linked to different base address, right? And this approach will allow us to, to copy the firmware to the second partition, and it will work. So, so now, what is the strategy? So the strategy is having two builds of the same firmware using two different linker scripts, and we need also to create a bootloader. So when we copy one partition, a new firmware to the partition, we also need to store some sort of a flag somewhere on the flash. Usually, it is kept at the very end of the flash. And that flag says what firmware to boot, right? And the bootloader just looks at that flag and, and just picks where should it jump? Should it jump to the beginning of the firmware 1? Or should it jump to the beginning of firmware 2? And that's it. So, and as you can see, this approach with these two partitions and two builds, it makes the bootloader code very, very simple. And that's very good, because the simpler the bootloader is, the better. And this allows to, keep the bootloader, as just one single instance at the beginning of the flash. And we may not even change it ever, because such a simple functionality is possible to implement without any bugs. Right. So I see a couple of questions. Let me answer them. So I'm so sorry. Yeah, that's right. So let me yeah, you're right. So let me share the whole screen. Yeah, I'm sorry about that. Okay, so I'm sharing the whole desktop now. So now you should see the whole desktop. Right, so please let me know if you cannot see that, right? So you should see the whole desktop. And done. Okay, so now let me repeat quickly so you can, yeah, thanks for telling me that. So this is a firmware I was talking about, right? So this is a really simple firmware. And this is the linker script of this firmware. So as you can see, it defines like two memory regions. And when we make this firmware, so the firmware.elf is created as a result of the build. And if we obj dump -d the firmware.elf, so disassemble, then if we search for the main function, here's the main function, you can see that this function starts at the address 08000022C. So it's basically in that flash region. So that's what I wanted to show you guys, right? So I hope this is now clear, right? So that's how linker script work. So GNU linker scripts, as you can see, they're not like really difficult to understand. They are somehow cryptic. Other tool chains have different ways of specifying where every section goes, right? So, and again, what I was telling, to implement the strategy with two partitions and two different builds, we need to have two linker script files. So basically link1.ld and link2.ld. And one linker script file has a flash origin starts at the beginning of the flash, and the second linker script file should have this origin starting at the middle of the flash. So, and then we build the same code using two different linker scripts. So yeah, that's pretty much it. So I can probably do that, like cp link ld to link2.ld, right? So, and then vim link2.ld to, so that should be this address plus one megabyte, because the length of the flash is one megabyte. I don't know exactly, like in hexadecimal what's 1 megabyte, but assume it's something like this, okay? So I probably wrong, but assume it's that. So we have two linker script files now, and we have one code, right? So we do make and we build the firmware.elf make clean, right? So we make one firmware link to the beginning of the flash, and then let me copy the whole command line, and we have firmware2.elf and use, so this is the argument, minus t link2.ld, right? So, and here I built the second firmware using second linker script file. So now I have two firmware elf files. You see, they are equal in size. They are also equal in functionality, but they are linked to different addresses. So if I do obj dump minus d firmware2.elf and search for function main, that you see the address of the function main, it starts from 801.022c. So to the, it's shifted to the, the offset that I specified in the linker script file. So I hope this is clear to you. And this whole strategy is also clear to you. So I do not describe the mechanism on how exactly the flash gets, the firmware gets written, because with this strategy, writing the new firmware to the second partition, it could be done like by by a working firmware itself. So the working firmware on firmware 1 can present some sort of like mechanism or UI or something for the user to push a new firmware, and the firmware 1 can copy this to flash region. So so the copying logic is not in the bootloader. Bootloader only decides which partition to boot. So that's the simplest scenario. Let's take a look. Can we do even a simpler scenario? So we have a working firmware, which is in Flash, right? In this diagram, it's written as, the Flash region is in gray color, and RAM region is in the cyan color, right? So the firmware 1, a current firmware, works right now. And what we can do if we have a lot of RAM, or if the firmware size is really small, so basically if we can fit the whole firmware into RAM, we can just load that firmware into RAM and then just replace the firmware 1 on Flash with firmware 2 and reboot. That is even simpler. So we don't need to keep the second version of the firmware, the second build. We just replace it. So what is the caveat with this approach? So the problem with this approach is that when we copy the firmware to Flash, usually the function that does the copy, it's specified in the firmware code, so it is in Flash. So basically, the function in Flash will eventually will erase itself and copy over something else, right? So the solution for this is that the copying function should be in RAM, should not be in Flash. And then during this copy, the interrupts should be disabled. Why interrupts should be disabled? Because the interrupt handlers, they are usually also defined as functions and as functions in Flash. So if during the copy we trigger an interrupt which calls the Flash-based interrupt handler, it will probably crash. So we need to disable interrupts. Also, there should be no power offs during the copying process. And this whole thing, this whole mechanism does not provide any way of rolling back the firmware. So if there is any trouble with this, we cannot roll back because we don't have a copy of the old firmware stored anywhere, right? So the other kind of bad property of this strategy is that the RAM should be big. So either firmware should be small or the RAM should be big, and it's quite a fragile mechanism to do this thing. So personally, I've seen implementations like this, but only kind of like as a test toy implementations to to test stuff. I haven't seen a single case in a production that use this. So I haven't seen. Maybe there are, but so I'm just describing this for you to kind of understand the possibility. Also, what I want to demonstrate is how exactly we can put a function in RAM. So what is the mechanism of putting function in RAM? So let me show that to you. So as you can see, the linker script file. So let's remove link to .ld. So an open link LD, right? So this is a linker script file, and you can see, so there are two regions, Flash and RAM, and this script, it says, put like different sections, and these names like vectors, text, arrow, data, and so on, these are so-called ELF sections. So when we make a firmware.elf, so usually the firmware binary is created in ELF format, and that ELF format has different sections. So code functions go usually in section .text. Data go in section called .data. Read-only data go to .ro data, and so on. So, but you can specify a section, an ELF section manually. You can do it yourself, right? So, and there is a mechanism for that. So, for example, if I open main.c, I look at my main function, there is a GCC kind of like a marker or trick, GCC attribute that tells to put that specific variable or function into a specific named section. So and the way to do it is attribute is called like is done like this: attribute and section, and then the name of the section. So let's say usually it's called IRAM, instruction RAM. So now when I type that, that makes my main function go into a specific ELF section. So now if we change our linker script to put the IRAM sections to data to the data part of the memory. So IRAM and dot IRAM star, right? So you see, I said here, what I said is that I want to group all ELF sections with name IRAM or IRAM dot whatever into the data big segment. And that big data segment goes into RAM. Here, it goes into RAM, okay? So now if I compile my binary again, and if I obj dump minus d firmware.elf, and then search for main function. So now you see my main function starts from the address 2000, which is the base address of RAM, of memory, right? So it's not flash anymore. So this trick that I've shown you right now, it allows you to put any function or any variable, like variables they go by default to data. So there is no reason to put it into the data sections. Usually people put variables into specific section so they can, for example, if your microcontroller has different memory regions, so starting from different like origin, you can specify in the linker script, you can say my specific like section name, and you can route that specific section name into a given memory region. So usually that's the for the data, people use that trick. But for functions, you basically just select any name and put that name into the data section here. And now the only question is left: who copies the these data, that data section to RAM, right? Because when we have a firmware on flash, our firmware is concatenation of text, of functions, and data. But it's a binary, it's a bin file, it's just one file, and it resides on flash, right? So what copies that? And the answer is the startup code, the microcontroller startup code performs that copy. So if we open the this bare metal programming guide that I'm just pitching so hard here. So if we go to scroll to the section that says about, that tells about, here it tells about linker script, and so this is a section called startup code. So this section explains how it's done. So the startup code, it copies the data section to the memory. So the startup code takes the data section, the data kind of segment from flash, and copies that into the RAM, right? So this is done by the startup code at the microcontroller boot. So for example, if we go and if we take a look at the startup code that is provided by the microcontroller vendor, so we are looking at the CMSIS device H5. So this is ST Microsystems provides the CMSIS package for all H5 devices. And if we go to source templates, GCC, here is, you see startup underscore STM whatever. So if we open any of that assembly file, that this assembly file has instructions, loop, copy data in it, copy data in it. So this pieces of code, they copy the data section to RAM. And this piece of code fills zero BSS, it nullifies the BSS section. So I hope this is clear to you now. So what I want you to understand after this is how exactly we can put a function in memory, what is the mechanism, and how linker scripts are used for that. And just one note about this. So if you put a function in memory, that means all the functions that this function calls also should be in memory, right? Because otherwise there is no point. If that function in memory calls another function which is still in flash, it will crash anyway. So So usually these functions, they operate in memory, from memory. They tend to be like really small, kind of well tested, really small, without any kind of like debug, print, leftovers, and so on. Okay, so I hope this is understood. So yeah, so let me, is that, so I described that, right? So where was I? 2 builds in place copy. So I described that. I described RAM. Yeah, so here, the next one, the variation of the how we can still how we can build a new firmware, but we don't have enough RAM, right? But we still don't want to have 2 builds. We don't want to have 2 builds of the firmware. So there is a variation strategy that that works like this. So during the firmware update, we copy the new firmware to the second partition. Okay, so we have that the firmware on the second partition, and then we make a flag, we make a mark somewhere on the flash saying we have a new firmware to boot, and we reboot. And when we reboot, the bootloader, it takes this, it looks at the flag and says, oh, I have like firmware 2, a new thing that I should boot. So the bootloader then goes and swaps firmware 1 with firmware 2. So that's what it does. So it gets these like 2 blobs of flash data and swaps them. Usually the way to go is to use like some scratch sector, because flash memory, unlike RAM, it can be rewritten only if it was erased before, right? So when flash is erased, it's all logic 1, right? And then after that, you can write to flash. So you can turn logic 1 to logic 0s. And once it's written, you cannot rewrite it anymore. You need to erase it again. And you can erase the flash only per sector. So you cannot erase a single byte or a single like word. You can erase the whole sector. So that's how like flash kind of flash erasing and writing works. So then you create a scratch sector, you erase that scratch sector, write one sector from firmware 1 to the scratch sector, write erase that sector from firmware 1, write a sector from firmware 2 to the place of firmware 1, and then write from the scratch sector to the firmware 2. So this is the way it's done, using these kind of like temporary scratch sectors. So but what is with this? So with this approach, we also have the bootloader function that does the copying of the flash, the flash swapping, also RAM resident. So it should fully reside in RAM. And again, the interrupts should be disabled for the same reason. We don't want any flash code to be executed during the copy. No power offs. And that, well, actually, it can be made even resilient to power offs if the copying logic is clever. It does checksumming, it writes the state. It can be resilient to power offs as well. So, and rollbacks are possible with this approach because we save the old firmware to to the second partition. So with this mechanism, it is possible to write a power off resilient copy mechanism, and it is possible to write like a rollback mechanism. Usually the rollback mechanism is implemented like this. So the firmware starts, and when the firmware starts, a new firmware starts, the bootloader starts a hardware timer for a certain period of time, and then, for example, like 2 minutes. Right, so it starts the timer for 2 minutes, and it writes a flag somewhere in the flash. It makes like it makes a flag. Oh, it might not be in the flash, could be like anywhere. That this firmware is kind of testing. It's not verified firmware, And if that flag is not changed during this 2 minutes timer interval, then the bootloader triggers the timer. And if the flag is still kind of like not modified, that means that something is wrong with the firmware. So nobody or nothing has set this flag to verified. So neither human set it to verified, neither like firmware code or some automatic code did set it. So maybe there is something wrong. Maybe the firmware hang or like went into like infinite loop or crashed or whatever happens with this, right? But the timer, when it triggers, if it sees that there is the flag is not set, that the firmware is bad, and it triggers this mechanism to swap the old partition back, right? So this mechanism with the hardware timer, it allows to make a really resilient rollback mechanism. So what I mean is that with this functionality of hardware timer and rollback and the like clever copying, swapping logic using states and so on, it is possible to build a very robust, resilient firmware update functionality, like using just 2 flash partitions, right? So it's possible to do. And obviously there are implementations to do that follow this strategy. For example, ST microcontrollers provides its own kind of software that comes together with the Cortex trust zone. So they provide their own software for the trust zone, right? And that trust zone sort of like ST functionality has OTA update functionality too. And that follows this strategy. So they do this mechanism that I've just described, right? So let me like go ahead and describe the next strategy. And the next strategy is kind of a cool one. It's a modern one. It's called the dual bank flash approach. So what is the catch here? The catch here is that many modern microcontrollers have a flash memory which is dual banked. What does that mean? It means that the flash is divided into 2 equal parts. They are called banks, right? And when a flash memory is mapped into the system memory, a certain register in flash controller, certain register is responsible for the mapping, for the order of the mapping. So by changing a register in the flash controller, you can map first bank first, and then the second bank follows, or vice versa. You can map the second bank first, and then the first bank that follows that, right? So basically with this one single kind of flip of the bit in the flash controller, you can remap 2 partitions of the bank, 2 banks of the flash in the order that you want, in the kind of like usual order or the reverse order. So that's usually on ST micros, it's just one single bit in the flash controller. So it's either 0 or 1. If it's 0, it's usual order. If it's 1, that is, like banks are swapped. So this thing allows to implement a flash update, like a firmware update, in a really, really simple way. Because what we can do, we can just copy the second firmware to the second bank, and then flip this bit in the flash controller, and that's it, and reboot the box. And then we boot the second firmware, and that's it. The rollback mechanism is really simple too, because what rollback does is just flips that bit in the flash controller and reboots the box again. So it's, again, really, really fast, simple, and easy. So and like, yeah, we don't need to have like a swapping functions that swap those partitions. We don't need to buffer those, say, big sectors if they are big. So if during power offs, yeah, so we can always, like do all the checks, all the like checksums. So it's quite a robust mechanism. And yeah, and rollback is also possible using like the same mechanism I described you with the, with the hardware timer and the verification of the flag. But then the actual rollback, how do you roll back the partition back, does not involve any swapping physical or copy, just one bit flip, right? So it's pretty robust. So now I want to demonstrate you how that is done, this dual bank OTA approach in one of the applications. So, and what is that application? Yeah, so this page describes the algorithm of the dual bank flash OTA. So it says just get a new firmware, copy that new firmware to the second partition using any kind of transfer media, like a serial interface or HTTP, like any network, and then yeah, and then basically swap banks and reboot. So now what I want to do, so there is a question: can external memory like NOR flash can be configured into dual bank and implemented for case where the MCU flash is single bank only? Oh, I don't think so. All right. So if you have an internal flash in MCU and you have like an external flash, yeah. So yeah, the thing is that this dual bank flash, it controls the mapping in memory. Like if you take a look at the linker script file, right? So the linker script file says the flash is at this base address and has two megabytes in size. So that means that this address, the mapping to the system memory of the flash area, is done by the microcontroller hardware. So so that the microcontroller flash controller should do that. So the flash controller should know about banks. If you have an internal, like an external flash, I'm not sure that the controller can be configured to take on the external flash and map that to the system memory. At least I haven't heard, and I don't know about this. So but to my understanding, the answer is no. So the dual bank, it should be if the dual bank is supported, it should be supported by the flash controller that goes with the MCU. So with any sort of like external flashes, it's not possible. Right. So I hope I answered that question. So now the Mongoose library. So I want to demonstrate and make a demonstration on the H5 device. So here I have a development board. Here it's connected to my computer. So one part goes to Ethernet, so connected to Ethernet, and that goes to my workstation, right? So to the USB. So I have it connected to my workstation, and this is ST Micro H573DK. So it's a development, DK is, I think, discovery kit. So I'll use Mongoose library. So this is a library that is developed by our company. Why I'm using this library? So first of all, this is a library, kind of a Swiss Army knife to implement any networking functionality. So it's one single file, or well, two files, mongoose.c and mongoose.h. You copy these two files and you have networking implemented on your micro. You don't need a TCP IP stack. You don't need RTOS. Well, you can use RTOS. You may not use RTOS. It's up to you, but it doesn't need RTOS. And also it has a built-in TLS stack. So you don't need embed TLS or anything. So basically, you copy over these two files and you are done. So you can implement networking on your workstation. It's really simple, really nice. So and we have a bunch of examples for Mongoose. It has like a really great documentation guide. So if you take a look at this, so this is the site with the documentation. It has like everything, cool API reference, a lot of tutorials on many different boards. So so what I'm gonna use, I will use a pre-built device dashboard demonstration for this discovery kit, right? So what I'll do, I'll go and I basically clone Mongoose repository to my workstation, right? So I go to my home directory and I do git clone Mongoose. So now I'm cloning Mongoose, and then I want to build the firmware on it. Okay, done. CD Mongoose examples STM32. So as you can see, there are many examples on STM32. CD STM32 H573 make bare metal built-in. So this is the example. Make bare metal built-in means that the ID is make, not cube, not Kyle. It's simple make. The RTOS, there is no RTOS, is bare metal. And built in that we are not using LWIP, we are not using MDK, we are not using Zephyr, we're not using Azure, we're using our own built-in network stack. So as you can see, this is a simple bare metal firmware. It's really minimal. There are just only few files, right? So that implement this this thing, and what we do, and this firmware implements a device dashboard. It's and I'll show that to you right now. So if I type make, the make command, it pulls two CMSIS repositories. One CMSIS repository is from ARM. It's called ARM core, which describes the Cortex core. And the second repository is STM, ST Micro's H5 device. So we pulled these two repositories, and here we just built the single command builds the firmware.elf. So now we have firmware.elf and firmware.bin built, and now I want to flash them onto this device, right? So I need STM32 Cube programmer. Let me run the programmer. It starts sometimes slow. Okay, so now here's the programmer. I click connect to my device. All right, connected. And now I go here and browse. So I click on my home directory. I need to search for Mongoose. Where is Mongoose? Here's Mongoose, right? So Mongoose examples, STM32. Where is STM32, and then STM32 H573 DK make bare metal built-in. Here it is. So now I choose firmware.elf, click open, and click on start programming, right? So now it says okay, and I have the board blinking, because that's what this firmware does. So now what I need to do, I want to monitor serial logs. So now let me start the monitor. So I'm running the utility that monitors serial logs. So as you can see, now let me reboot the box. So I reboot the box, and the serial log, let me pull it over here. So the serial log, well, let me reboot it again. The serial log says that, okay, I've got the address from DHCP. So this is the address 192.168.0.93, right? Let me copy this address, go to my browser, and I put that into my browser, like so. I have this device dashboard UI. So I will not describe how it works, how the UI works. It's a topic of different webinar, which you might want to listen to. But Mongoose library allows to develop really easily UIs like this with the device dashboards, right? But one of the cool things of this device dashboard and Mongoose is it provides the firmware update UI as part of this reference dashboard, and the UI is the firmware update is actually implemented. So it's not a mocked UI; it's an implemented thing. So this firmware update UI actually work for this ST, right? So and now I'll demonstrate it to you. So let's see. Let's change something in the firmware. So let me start a new. All right, let me start a new terminal. So like CD Mongoose example STM32 H573 make bare metal built-in. So I open main.c. In the main.c, I'll change something. So let me change the message that is printed. So instead of Ethernet, I'll print Ethernet 2, right? So I save this. And I type make to make this. So now I've built a new firmware that prints Ethernet 2 instead of Ethernet here, right? So and now let me use not a cube programmer. Let me use this UI to push that new firmware to the board, to this board, right? That's what I want to do, to push that firmware, and I expect this message Ethernet to change to Ethernet 2. And this whole update mechanism is using dual bank approach, right? So let me do that. So I click on upload new firmware, and I choose my home directory, Mongoose, examples, or is STM32, STM32 DK make bare metal built-in. Here it is, firmware.bin. So I click on open, and now you see the UI says, okay, so it's done. And now in the UI you see, so we switch. So now this current firmware image is switched. So now we have like it's a different size, different flash in time, and so on. So I even can click on commit to commit this new firmware, and let's see at the messages. So we print different messages now, right? So let me shrink this browser window. So we print Ethernet 2. And now look, if I click on this button, roll back to the old firmware, if I click on that button, we execute rollback using this flashbang swap. It will be really fast. Look at this. So I click on this button, and here we go. So we rolled back. So we print Ethernet now. So you see the rollback procedure is kind of lightning fast because it's just a flip in the flash controller and just reboot. That's it. So I guess that's what I wanted to show you, ladies and gents, today. I don't think I have enough time to explain this more and like dive deep into the implementation of this like bank swapping OTA update, but I hope that what you heard today and what you saw was useful for you, right? So if you have any questions, please click on the question button and ask. I will answer. Otherwise, what I'll do, I will follow up after this presentation as we finish. I'll follow up with the email to every participant, and I will send the reference, the examples that I used, the slides, and I will also include the link to book a one-to-one consultation with me. So if you want to discuss any topic on the embedded networking or OTA, then please be my guest. So I want to I can be like of help, and I'll share any expertise that myself or my team has with you. So please don't hesitate. Book the consultation, and if there are no questions, and I don't think there are any questions, so then thanks a million for joining today's webinar. Hope it was useful, and yeah, I kind of advise you to book other webinars that we have on web UI creation and on smart device creation. So if these topics interesting to you, yeah, please go be my guest. Cool. So thank you very much, and see you later. Have a nice evening today. Bye bye.